I am Leah Wright,
And I'm Austin Bowman.
and we're talking about reaction stoichiometry. This is part 2.
If you haven't watched part 1 with Brandy, you need to go watch that now. Alright, the first thing we need to talk about is the mole ratio, which is really easy after you can do a few examples. So, to start with mole ratios, you need to balance your chemical equation, whatever it is. So here we have sodium phosphate plus potassium hydroxide yields sodium hydroxide and potassium phosphate. So we need to start with balancing our sodiums. So we're going to put a 3 over here. And then we have 3 hydroxides and 1 hydroxide, but 3 potassiums and 1 potassium. So all we need to do is add a 3 over here. And for mole ratios, I would write a 1 in front just because it helps. So the mole ratio is literally a product compared to a reactant, or a product compared to a product, or a reactant compared to a reactant with their coefficients. So if a question asked you what the mole ratio of sodium phosphate was in this chemical equation of sodium hydroxide, you would just look at their coefficients. There's 1 mole of sodium phosphate and 3 moles of NaOH, so it's 1 to 3. And another example, like on the same sides, sodium hydroxide to potassium phosphate would be 3 to 1. And it's hard to understand what you use these for right now, but we need to go over that before we do the problems. But it'll make sense once you get to the problems.
Okay, so for the second problem, you have the same number of magnesiums on both sides. So for right now, we don't have to add a coefficient. And then for lithium on this side, you have 2, and then on this side, you only have 1. So we're going to add a 2 right there. And then you see that you only have 1 carbonate over here and 1 carbonate over here. And now you have 2 fluorines and 2 over there. So you don't have to balance anything else. And you want to put the 1s just because it makes Austin happy. And just like he said up here, if you were comparing magnesium fluoride and magnesium carbonate, it would be like that. And then it would be a 1-to-1 ratio. Okay. And same thing for lithium carbonate to lithium fluoride. That would be 1-to-2 ratio because of your coefficients.
And they don't have to be on opposite sides. They can be on the same side. You can use mole ratios to compare anything as long as it's in the same chemical equation. So down here we'll have solid phosphorus reacting with oxygen to form diphosphorus trioxide. So these equations like this are easy because you have lone elements to manipulate. So you have 4 phosphorus over here and 2 right here, so you just add a 2 right here. And these are easy just because now you have 6 oxygen. You don't have to manipulate anything except for the oxygen, so you'll just put a 3 right there. So if you wanted the mole ratio of P4 to O2, you just look at the coefficients. It's 1 to 3. Or if you wanted O2 to the diphosphorus trioxide, that would be 3 to 2. Alright, so the first type of conversion you'll need to know in this unit is mole to mole. It's probably the easiest one. I mean, they're all easy, but this is the easiest. And this is the first time you'll have to apply the mole ratio. So the first thing you need to do, regardless of what this problem says, is balance your chemical equation. So you have 2 chlorines over here and 1 over here, so you need to add a 2. And then you need to add a 2 right here to do the sodium. Alright, so now you read your problem. It says, how many moles of chlorine gas would react with 5 moles of sodium according to the following chemical equation? And we've balanced it. Okay, so our known is that we have 5 moles of sodium. Our unknown is the moles of chlorine gas we have. So this is basic dimensional analysis. You've done this. The mole ratio, if it helps you, just think of it as a normal conversion factor that you would put in dimensional analysis. So you have 5 moles of sodium. Okay, your desired units are moles of chlorine, so we need to figure out a way to get from moles of sodium to moles of chlorine, and you guessed it, mole ratio. So our mole ratio is 2 moles of sodium to 1 mole of chlorine, so you just write that. 2 moles sodium, 1 mole chlorine. So now once you cancel your units out, what do you know? You have moles of chlorine left, so like any other dimensional analysis, you multiply across the top, divide by the bottom, and this would give you 2.5 moles of chlorine. There are 2 more problems on the note sheet you should have printed off, so go ahead and pause the video and do those now using this example as a reference.
Okay, so the next problem we're going to do is mass to mole, mole to mass. And first, okay, so the question reads, what mass of lithium phosphate would be required to produce 50 grams of lithium hydroxide? And usually you would be given your molar mass of lithium phosphate is 115.796 grams per mole, and lithium hydroxide is 23.949 grams per mole. So first you have to balance your equation, and since you have 3 lithiums over here, you're going to have 3 on this side. And you have 1 hydroxide and 1 hydroxide. And then you have 3 sodiums, so you're going to have to put a 3 over here now. And then you have 1 phosphate and 1 phosphate. So let's go over that again. You have 3 lithiums, 3 lithiums, 3 sodiums, 3 sodiums, 3 hydroxides, and then 1 phosphate on each side. So now you can go into dimensional analysis. So your known is the 50 grams of lithium hydroxide, and you're trying to find mass of lithium phosphate, which will be in grams. So first we're going to do 50 grams of lithium hydroxide. Okay, and since that's grams, you need to have your grams of, well, your molar mass of lithium hydroxide, which is the 23.949 grams of lithium hydroxide. Okay, and that's in 1 mole of lithium hydroxide. And then now you look at your equation and you see that for lithium hydroxide you have 3 moles, and then you're trying to get to your lithium phosphate, so you have 1 over here. Alright, so you're going to have 3 lithium hydroxide for every 1, well, just put mole. 3 mole of lithium hydroxide for every 1 mole of lithium phosphate. And then you're going to do, since you're looking for your mass, you have to find your grams of lithium phosphate, so you're going to do 1 mole of lithium phosphate. And your molar mass was 115.796 grams of lithium phosphate. Alright, and now all you're going to do is multiply across the top and divide by everything on the bottom, multiply together. So that would be 50 grams of lithium hydroxide times 1 times 1 times 115.796. And then you divide that by 23.949 times 3. And your answer should be 80.5851 grams of lithium phosphate.
And none of these answers are going to have sig figs because sig figs are stupid, but you need to do sig figs because she tells you to and she'll take off points. But you can adjust these yourself with sig figs when you do the actual calculations. So once again, there should be 3 problems on the note sheet that you should have downloaded and printed by now. So again, do the next 2 using this as a reference. And if you have any questions, watch this again and hopefully you will get it. Okay, so the next type of problem you'll probably encounter would be mass to moles to molecules. So it's really just like the last one, except you're going to end with molecules instead of mass using Avogadro's number. So once again, the first thing you have to do is balance your chemical equation. You have 2 O's on this side and 1 over here, so you're going to put a 2 right there. Not a Z, a 2. And then now you have 2 zincs over here, so you just put a 2 right there, and then you put a 1 right there because there's only going to be 1 mole of oxygen for every 2 moles of zinc. So it says you start with, the question reads, how many molecules of oxygen gas react with silver when forming 20 grams of zinc oxide? So that is our known, and this is our unknown. So we're going to start with the 20 grams of zinc oxide. So I've written for you the molar mass, and it'll be on your note sheets too. Of zinc oxide is 22.941 grams per mole. So 22.941 grams, 1 mole. And those are both zinc oxide. Don't forget your units, because when in doubt, make your units cancel. Alright, so we're trying to get to oxygen, so here we go with mole ratio again. So there's 2 moles of zinc oxide for every 1 mole of oxygen. So 2 mole zinc oxide, 1 mole O2. So now you have to use Avogadro's number, which states that for every mole of a substance, there are 6 times 10 to the 22nd molecules of that. Or excuse me, 23rd. Okay, so then you'll multiply that out, and I'm going to go ahead and do that real quick. So you have 20 times 6 times 10 to the 23rd, and then you would divide that by 2 times 22.941. That's multiplying. Okay, so that would give you 1.376 e to the 26th molecules of oxygen. So this is just like, I hope you're getting the gist now. There should be 2 more problems on your note sheet. So go ahead and pause the video right now and try and work the next 2 out using this video as an example. And again, if you don't understand it, watch this video again, and good luck. Okay, so our next type of problem is molecules or mass or volume to moles to volume. In this problem, I'm just going to show you volume because I feel like you're getting the gist of it at this point. So any other problem on your note sheet with problems would be the same thing, except you would start with molecules or mass, and I honestly think y'all get it at this point. One thing we need to talk about before we go over this problem is when you're converting from anything to volume with reaction stoichiometry, it has to be gases at standard temperature and pressure. If it's not, then then you can't do it. So it has to be gases at STP. So our problem reads, how many liters of water can be made from 5 liters of oxygen gas with excess hydrogen? We'll talk about this word excess later, but for now, don't worry about it. Alright, so first we need to balance our equation. We have 2 H's over here, 2 H's over here. We're good. But we only have 1 O. We have 2 O's here, so we're going to need to add a 2 right there. And then we'll need to add a 2 right here to then balance our H's. So now we're completely balanced, and we'll be able to get our mole ratio. So we're starting with 5 liters of oxygen gas. And this problem should say at STP, but I'm telling you, it's at STP. All your problems will say at STP. So you're starting with 5 liters of oxygen gas. And the equivalents, which y'all might have gone over and you might not have, any 1 mole of gas, it doesn't matter which gas it is, at STP occupies 22.4 liters. That's for any gas. It's not like mass. 1 mole at STP is 22.4 liters. You need to memorize that conversion factor. Okay, so then we plug in our mole ratio, and that is, we're going from oxygen to water, so we say 1 mole oxygen, 2 mole H2O, And then again, this water in this case is going to be in gas form, not in liquid. So you're going to say 1 mole H2O is 22.4 liters H2O. Okay, so now all we have to do is calculate that. So, just normal dimensional analysis. On the top, you're going to say 5 times 2 times 22.4, and then you're going to divide that by 22.4. And you might have noticed these just cancel, so really you can just say 5 times 2, but for those of you who want 100% correctness, I would add the 22.4s just in case. You don't want to get in the habit of just skipping things. So, like I said, you just cancel those out. 5 times 2 is 10. So your answer is 10 liters of water. Alright, the next thing we need to talk about is limiting reagent, and this is going to be really important the farther you move in because you're going to need to know what the limiting reagent is for really every problem after you start talking about it. So basically, the limiting reagent is the reactant that forms the least amount of product. So if you have, let's just say, like 1 mole of this and 1 mole of that, they're both going to form 1 mole of this, but that's not the case. So the limiting reagent is whatever produces the least amount of a certain product. So how you do this is you set up two-dimensional analysis using each reactant. But first you need to balance the equation. So you have 2 H's over here and 1 over here, so we're going to balance this. Put a 2 right there. And we have 2 chlorines right there. And we have 1 calcium and we would need a 2 right there because you should, when you're doing acid base, you should really write water as HOH because you're going to have to balance hydroxide sometimes. But that would look like that. So you have the 2 H's and you just put a 2 right there. So now your H's are balanced and then your hydroxides are balanced. So you make up your own units for the first one. Let's just say you have 1 mole of each. So you have 1 mole calcium hydroxide, and that's from up there. But if it just asks you what the limiting reagent is and there's no other question there, then you just make up something. Okay, so then you also say 1 mole hydrochloric acid. And you're going to convert these to the same product so you can see which one's going to form the least amount of product. And the one that does that is your limiting reagent. So you look at your mole ratio. We'll just convert it all to calcium chloride. Oh, and that's what they're asking for in the problem too, so that's convenient. Okay, so for every 1 mole of calcium hydroxide, there is 1 mole of calcium chloride formed. And for every 2 moles of hydrochloric acid, there's 1 mole of calcium chloride. And again, those are just the mole ratios. So when you multiply that out, you'll get 1, but down here, you're going to get 0.5. So because you only get 0.5 from this, that's the maximum you can get with 1 mole. So hydrochloric acid is your limiting reagent. So this problem actually read in the following reaction how many moles of calcium chloride are formed if 1 mole of calcium hydroxide and 1 mole of hydrochloric acid are allowed to react. Well, luckily, to figure out the limiting reagent, which was the second part of the question, we used 1 mole. So really now all you have to do is look. The most you can form is 0.5, so that is not only the answer to the second part, but the first part too. So there should be 3 problems on your paper. Pause this video now and work out the next 2. And if you need help, come back to this one. The next thing we're going to talk about is excess reagent, which is really easy if you understand limiting reagent. Alright, so the next thing we need to talk about, next to last thing, almost there, is excess reagent. And excess reagent is really the opposite of limiting reagent. It's what you have, well, I don't want to say too much of, but more than enough of. So I'm using the same chemical equation we used for limiting reagent just to kind of make it simple on you. But there will still be 3 new problems on your worksheet, but you should be able to use this to solve them. Okay, so if you it wants to know what the excess reagent is from the get-go, then you're going to have to find the limiting reagent first, and you already know that. So from our last section on limiting reagent, we determined hydrochloric acid was the limiting reagent. So, and we figured out, since it's the limiting reagent, only 0.5 moles of calcium chloride would be formed. So now basically what you do is you start at the product you use to find the limiting reagent and just go back to the reactant that was not the limiting reagent. So what you would do is start with 0.5 moles calcium chloride. Then you would go straight into your mole ratio, and it's 1 to 1. So you get 0.5 moles of calcium hydroxide. So basically what that means is, after this reaction has completely taken place, since hydrochloric acid is the limiting reagent and you can only form, and you only use half of that calcium hydroxide, then half of it's still left over. So if that were to actually happen, you would still have 0.5 moles of unused calcium hydroxide. So our last video is going to be on percent yield, so get excited. Last section.
Okay, so the problem is about percent yield, and
I'm sorry.
the problem says aluminum reacts with an aqueous solution containing excess copper 2 sulfate if 1.85 grams of aluminum reacts and the percentage yield of copper is 56.6%. What mass of copper is produced? So, first we know that this is your known, and your mass of copper is your unknown. So first we're going to just do, first we have to balance the equation, right? So we have 2 aluminums on this side, so we got to put a 2 over here. And then we have 3 sulfates, then we're going to have to put a 3 in front of that. And since we just put a 3 in front of that, we have to get 3 coppers. So we have 2 aluminums, 3 copper, 3 sulfate, and 3 sulfate. So it's balanced. And, okay. And, alright. So now we're going to do dimensional analysis. So we know that we start off with 1 point, okay, yeah, I'm going to do this one.
Yeah.
Okay. That's not writing. 1.85 grams of aluminum. And that goes to, so the molar mass of aluminum is 26.98 grams in 1 mole. And then when we look at our equation, we can see that there are 2 moles of aluminum for every 3 moles of copper. And then since it's asking for the mass of copper, we have to change that to grams. So in 1 mole of copper.
Okay, that says 1 mole of copper. Our marker's done, but
That's 1 mole of copper for 63.55 grams of copper. Alright, and then once you multiply that out and everything and divide, you're going to get 6.53 grams of copper.
But wait.
Okay, so now you have your grams of copper, but it says that your percent yield of copper is only 56.6%.
Which basically means that you're only going to get, this is what you should get, but due to whatever reason, if this was in lab, you're only going to get 56.6% of what you should get. So what you have to do is
multiply by 56.6%.
Which is 0.566, just in case you're a little bit iffy on percentages.
So that's supposed to be a multiplied sign. And it will be
0.566.
And so your final answer is going to be 3.69 grams of copper.
And that's Reaction Stoichiometry. I'm Austin Bowman.
And I'm Leah Wright.
Good night.
You have to think about that. She's like, and
You have a text from Amber.